Okay, now we're going to our next lab, the lab on tides. Okay, let me share my screen. Okay, so we'll hit this one here. Tides and tidal forces. So introduction. Okay, this lab investigates the origin of tidal forces and compares the tidal forces on the Earth that are caused by the moon and the sun. So not a lot of people realize that the sun also causes some tides on the Earth, even though the moon is more dominant. The moon is the primary reason that we have tides, but the sun also causes tides. So it also investigates the role played by tidal forces in the formation of astronomical bodies through gravitational accretion. Daily changes in sea level heights are caused by the variation in the gravitational force exerted by celestial bodies on different parts of the Earth. Such differential or tidal forces also have other important effects in the solar system and elsewhere. So the learning objectives: describe how tidal forces result from gravitational force, describe why the Earth has tides, define the Roche limit, and explain why it occurs. Okay, so now go back to the previous one. Okay, so Newton's law of gravitation. The further apart two objects are, the smaller the gravitational force exerted on one by the other. According to Newton's law of gravitation, two masses m1 and m2, separated by a distance r, exert a gravitational force one upon the other. In other words, m1 pulls m2 and m2 pulls m1. These pulls are the same strength, but go in opposite directions. Remember that force is a vector, meaning that it has both magnitude and direction. The relationship among these quantities takes the form of the relation shown where g is the gravitational constant. So essentially what this is saying is, as the distance of the objects gets further apart, r is the distance between the two masses, then the force of gravity decreases as 1 over the distance squared. So if I take this, let's say, if I take this twice as far away, right? So let's say their distance from here to here was a certain distance. And if I double that distance, let's say somewhere here, the force of gravity should go down by a factor of 4. If you double the distance r, imagine putting a 2 there, and then you square that, you get a 4. So the force of gravity goes all the way from some number all the way to 1/4 of that number. So it drops drastically. Okay. So the easiest way to think about tidal forces is as a stretching force, pulling close objects and pushing away far objects. The tidal force exerted on a small part called ms of a large mass, big M, at a given location is an example of what we term a differential force. It may be approximated by taking the difference between the gravitational force exerted on ms at its actual location and the gravitational force that would be exerted on ms if it were located at the center of the mass, m. Gravity depends on the inverse square of the distance d between the two bodies. So the gravity exerted by m2 on ms is larger on the side of m closest to m2, point A, than on the opposite side that farthest away from that is farthest from m2. So let's see here. Imagine that there's a little portion. Imagine that this is a planet. So think of this as a solid planet, not an empty planet. So just think of it as filled in. So imagine a little portion of that planet if that little portion is on this end, it's going to be attracted by that object with a great force, right? With a great force. And if that object is at point B, then it's at the center, then it will be attracted with a somewhat, to show, note that by, let's see here, if we go to point C, then it's going to be attracted by that object with a less force. So what they've done here, they haven't really shown exactly. I'm going to share the whiteboard. So imagine the moon is here. So imagine this is the moon, and then imagine this is the Earth. Okay, so now if the point is here, that MS, right? That little portion of the Earth that's here, the moon will attract that with the largest force. So I'm going to draw that vector with the largest length. Then it's going to attract, if that little piece was in the middle. So I'm just going to give this some numbers. Let's say the moon were to attract, this is the moon. Let's say the moon were to attract this with a force of 100 newtons. I'm just making up the number. Then if that little mass was here, let's say the moon was attracting it with a force of, let's say, 90 newtons. And let's say that little mass is here. So let's say that little mass is here. And the moon is attracting it with a force of 80 newtons. So what's the effect of that? Because the gravity is always attractive. So it's attracting all of it. But now let's just focus on the Earth now. If a certain portion of the Earth is being pulled to the right by 100, and the same little mass at the center is being attracted by 90, and the same mass here is being attracted by 100, what's the Earth gonna feel like? Okay, so now here's what I'm gonna do. I'm gonna call the force on the center 0 newtons for a second. So imagine calling this force, this force here is 0. So with respect to the center of the Earth, with respect to the force that the center of the Earth, so let me word it this way. With respect to the force that mass would have felt if it was at the center of the Earth, let's make that force 0. If that mass was at the right side of the Earth, you would feel a net force of 10, right? In other words, 10 newtons greater than the force that you would feel if it was at the center. You see what I'm doing? I'm making the center the reference point. I'm saying if that mass were to be at the center, it would, let's assume that force is 0. If that mass is on the right side, closer to the moon, you would have the effect of feeling an extra greater 10 Newton force to the right. Now, if that mass was on the left side, farthest away from the moon, okay, then you subtract 80 minus 90 and you get negative 10. So it has the effect of being pulled to the left by 10 newtons, right? So with respect to the force that mass would have felt if it was at the center, that same mass being at the two ends is being stretched. So essentially what that means is that the tidal force of the moon on the Earth is going to cause the Earth to sort of go like this. I'm going to exaggerate a bit here. It has the effect that the Earth is going to bulge out like this. So this is the moon right here. You see? So the moon will have a tidal effect and it will bulge out. Of course, I am exaggerating here. The tidal force of the moon on the Earth is not that strong to make the Earth be egg-shaped like that. But if we take this Earth and imagine the Earth here, so imagine that this is the actual Earth, even though the moon doesn't have the power to make the Earth itself bulge out that much, it maybe bulges out a tad bit like this. But because it has bodies of ocean water, which are more possible to bulge out, therefore that ocean body of water will bulge out. You see? So then this is the oceans. You see? Like that. So you see where high tides come from? The side of the moon, the side of the Earth facing the moon will be high tide, will experience a high tide. And the side of the Earth that is away from the moon will experience a high tide. So that's where the origin of tides come from. Now the Earth will also cause tides on the moon, but since the moon is not too large, the tidal force of the Earth on the moon is not as large as the tidal force of the moon back on the Earth. The tidal force of the moon on the Earth is stronger than the tidal force of the Earth on the moon because the moon is small, you see. The smaller the object is, there is not much difference between the front end and the back end. And so it doesn't get bulged out. So it's kind of interesting in this case that the moon, if you consider this like almost like a fight between us, the force of gravity of the Earth on the moon and the moon on the Earth are equal. So in that battle, we are tied. But in the battle of tides, the moon beats us. The moon causes greater tides than we cause on the moon. You see? So now that's kind of a little bit more detail of what they're showing you here. So you see what they're doing is they're already considering so they're already considering the center as being zero. And then they're saying if that mass, with respect to being at the center, if that mass is over here, it has the effect of being pulled away. And then if that mass is at all points, oh, okay. So you see, at the front end, it gets the effect of pulling this side. At the center, that's the reference point. So then that's what they're showing there. Okay. So the magnitude of the tidal force can be derived from the expression for the gravitational force by using basic calculus. So this is kind of why one of the reasons Newton invented calculus is that he wanted a way to find out the force of gravity on planets and the sun and the moon. And he found out this equation. He sort of discovered that equation. And then he also found out the tidal force equation, 2 times the radius of the Earth over the distance times Fg. And now you could say, well, the sun also has a tidal force on the sun has also a tidal force on the Earth, but it's smaller than the tidal force of the moon on the Earth. Why? Because the sun is farther away. So the easy way to say it is the front end of the Earth is not that much closer to the sun than the back end of the Earth, you see, because the sun is so far away. So the tidal force of the sun on us is smaller than the tidal force of the moon on us. But the front end of the Earth is a lot closer to the moon than the back end of the Earth because the moon is closer, you see. So by taking the ratio of the magnitude of the gravitational force exerted on the Earth by the sun to that exerted by the Earth by the moon, we obtain equation 3 in the box. Similarly, by taking the ratio of the magnitude of the tidal force exerted on the Earth by the sun and the tidal force exerted on the Earth by the moon, we obtain equation 4. Note that for equations 3 and 4, the ratios depend solely upon the masses of the sun and the moon and their respective distances. So gravitational forces exercises. Okay, using the data above, determine the ratio of the force of gravity pulling on you from the sun to that from the moon. Okay, so they're saying here the force of gravity of the sun. So they're giving you here the distance of the Earth to the moon, the distance of the Earth to the sun, the mass of the sun, and the mass of the moon. So how would we find the force of gravity of the sun divided by the force of gravity of the moon? So that's going to be this one. So they're giving you equations for force of gravity, tidal force, the ratio of the force of gravity of the sun to the moon, and the ratio of the tidal force of the sun to the tidal force of the moon. Okay? So let's say if we wanted to use this, for example, I'll give you one example. So okay, let me show you this for an example other than the one that we had here. Let's say I wanted to find out the force of gravity of the sun on Jupiter divided by the force of gravity of Jupiter and its moon, you know. So we could use that as an example. Take the ratio of that. So then we would go force, so Jupiter planet. Probably a lot of mythology came up. Okay, so what would we have to know? We would have to know the mass of Jupiter. Okay, so this is the mass right here. So 1.8982 times 10 to the 27th kilogram. So how would we do that? So let me take a picture of that. So what else do I need from that formula? I need to know the distance of the Jupiter to the sun, right? Jupiter, distance of Jupiter to the sun, where is that? They're giving it to us here in semi-major axis in gigameters. Yeah, right here. So this is the distance of Jupiter to the sun, 778.57 gigameters. I'll take a picture of that. And then what else do I need? I need a mass of the sun, which is already given here. I don't know why they're giving in grams. That's kind of unusual, but it probably doesn't matter. And then the mass, then I would need the mass of the sun, the ratio of the force of gravity pulling on you from the sun to that from the moon. Okay. So hold on, we're trying to find the ratio of the force of gravity pulling on you. So imagine you were living on Jupiter. Oh, okay. If you were living on Jupiter and we wanted to find the force of gravity on you from the sun, right? Divided by the force of gravity on you from the moon of Jupiter. So that's the better way to do it. So that's kind of what they want to know here. The force of gravity on you from the sun. So we would need to know the mass of the Jupiter sun distance we already know, right? And then we would need to know the Jupiter moon distance. Okay, so we don't need the, let's see here. Yeah, so let's go to the moon of Jupiter. Let's say the famous moon Ganymede, which is actually the largest moon of Jupiter. Ganymede moon. So this is how many kilometers it is away from Jupiter. 1070. And then we would have to know the mass of the moon, which is this guy right here. 1.4819 times 10 to the 23 kilogram. So then how would we do that problem? So then we would do mass of the sun, distance of Jupiter to its moon squared over the mass of the moon of Jupiter divided by distance of Jupiter to the sun squared. Okay. So let me erase this so you can see what we're trying to do here. So if this is the sun, and this is Jupiter, and this is the moon of Jupiter. So basically, if you were standing there, you yourself, so we want to know the attraction of the moon of Jupiter to you, and then the attraction of the sun on you. So what's the ratio of those two forces? Which force is greater? I think the moon of Jupiter probably will pull you stronger than the sun will pull you, because the sun will be so far away by that point. So that's the ratio we're finding. We're not comparing that to the pull of Jupiter on you. That's a different thing. You see, we're comparing the pull of sun on you and the moon on you. So then we're trying to see that's the ratio. Let's see, force of gravity of the sun divided by the force of gravity of the moon. So force of gravity of sun over force of gravity of moon. So then your mass won't matter, because we're just taking ratios. Your mass will cancel out. So then you're just going to have mass of the sun times the distance squared of the Jupiter to the moon, of Jupiter, and that's Ganymede we're using as an example, divided by the mass of the moon times the distance of Jupiter to the sun. Yeah, Jupiter to the sun. Jupiter to the sun squared. Because you're standing on Jupiter, so if you want to know how much the sun is attracting you, you need to know the distance between you and the sun. So the mass of the sun, they gave it to us in grams. So let's write that down. 1.989 times 10 to the 33 grams. 1.989 times 10 to the 33 grams. Divided by the mass of the moon. I wrote it. Oh, no, I took a picture of it. Hold on. The mass of the moon was 1.48. 1.4819 times 10 to the 23 kilogram. Okay, what was the distance of Jupiter from its moon? That one was 1070,400 kilometers. So that's the distance of Jupiter to the moon. Then you square that. Then you divide that by what was the distance of Jupiter to the sun? Okay. Well, I wrote that originally 778. 778.57 gigameters. Then squared. So here part of the difficulty is with all these the kilos, grams, kilometers, gigameters. So to do that, it's better just to make everything the same. So for example, we can keep this one as grams. So write 1.989 times 10 to the 33 gram. And then this one will go 1.4819 times 10 to the, since 1 kilogram is 1,000 gram, this is going to be multiplied by 1,000 to convert to gram. So then this is going to be 10 to the 26th grams. You see, so you multiply this by 1,000 to convert to gram. And then what I could do is I could put these under the same parentheses. Then I'll have 1070,400, and then a kilometer is 10 to the third meters. And then here, 778.57 times, and then a gigameter is 10 to the 9th meter. And then we square that. Right? So then what ends up happening, the meter and the meter cancel. And then gram cancel. So the idea is for the ratio that it should be a unitless number. So then 10 to the 33 divided by 10 to the 26, what do you do with that? You subtract the powers and you get 10 to the 7th. 33 minus 26 is 10 to the 7th. Okay. And then here you can do 10 to the 3rd over 10 to the 9th. And then what's that going to be? You subtract 3 minus 9, you get 10 to the minus 6. but you're squaring that. You're squaring the 10 to the minus 6 because it's inside the parentheses, right? So when you square 10 to the minus 6, you get 10 to the minus 12. So this being turns into 10 to the minus 12. So scientific notation here, right? And then 10 to the 7th times 10 to the minus 12 is going to be 10 to the minus 5. So my answer is going to be whatever I get, I have to multiply by 10 to the minus 5. So now let's do these numbers on the calculator. 1.985 divided by this. Then I'm going to take the ratio of this and then square it. So let me do that first on the calculator. Take the ratio of these two numbers and square, then multiply it by the ratio of those two numbers. So then it's going to be okay. So then it's going to be online calculator. You know what? Let me go back to take a picture of the whiteboard. Okay, so I'm going to do 11070 divided by 778.57. So that's the stuff in the parentheses. Okay, then square that to the power squared equals. So you get this big gigantic number. Then you multiply that by the ratio of 1.989 divided by 1.4819 equals. Then you multiply that by 10 to the minus 5, right? Yep. 10 to the 7th times 10 to the minus 12, 10 to the minus 5. So multiply that by 10 to the power negative 5. Oh, 25. 25.4. 25.4. Ooh, so what does that mean? It came out like a decent number. So that means the force of gravity of the sun, even with the 10 to the minus 5, so it came out 25.4. Oh, I'm actually surprised. The force of gravity of the sun on you is still 25 times larger than the force of Ganymede on you, the force of the moon. Of course, the force of Jupiter on you will completely kill both of them because Jupiter is very, very heavy and you're sitting right on it. So the force of Jupiter will completely dominate both of those two forces. But the force of the sun on you versus the moon on you, the sun is still winning, but just by 25 times. I thought the moon would win. Very curious. So probably when you go to the even more outer planet, then the sun might lose. Like if you go to Saturn. That was curious, very interesting. You always learn something every day, right? So basically for those ones, you do have to show work nicely and neatly like I showed here. So show work for this and then answer it and then take a picture of if you got it right or wrong. So also show work. Then go to the next one, show work for that, submit, and then show whether you got it right or wrong. Then go to the next one, and then that's just the more ordering one. You just put the order, and then you don't need to show work. Just take a picture of each one, 1, 2, 3, And then for those first two, well, for this one, you're actually comparing the tidal forces. So you use this next equation right here. Whereas the first one, you're comparing the gravitational forces. So one of the things you should find here is that the tidal force of the sun on you is going to be less than the tidal force of the moon on you. So that's, in other words, this ratio should be less than 1 if you do it correctly. The sun causes less tidal force than the moon. But the first one, the gravitational force of the sun on you, I believe should be more than the gravitational force of the moon on you. Well, of course, if Jupiter, if it was still more for Jupiter, this number should be pretty big, I think. Very, very big. But this number should be less than 1. Okay, next. Oh, I think that's it for this one. Okay, so then you go to the next one. Tides on Earth. Oops. Tides on Earth. Okay, tidal forces. Oh, so they're talking about those tidal bulges, kind of like I explained. So I'm not going to read this because I kind of explained that. See how you get the tidal, the pooling like this. And so the side facing the moon will have high tide, and the sun, the side facing opposite to the moon, I mean, not opposite will have high tide, but at 90 degrees, you'll have a low tide. High tide, high tide, low tide, high tide, low tide, high tide, low tide, high tide, like that. So the tidal forces from the sun can augment, that means add to, it can increase the tidal force from the moon, producing spring tides. This has nothing to do with the season spring. So it happens twice a month when we have when we have full moon and new moon. So it says, or the two of them can cancel each other out, producing neap tides. So you see here what's happening. Although the sun exerts a greater gravitational force on the Earth than does the moon, the sun is so far away that its force does not change very much from one side of the Earth to the other. Since the tidal force is a differential force, the tidal force caused by the sun has only about half as much effect as the tidal force caused by the moon. So you see, neap tides occur when the moon is at first quarter phase or third quarter phase. So when it's, you see now, notice on that day, the high tide is high, but the low tide is also kind of high. So there isn't much difference between low and high tide. The sun is causing, quote unquote, the low tide, right? But it's not that low. And the high tide is not that high. But on spring tides, that occurs when the moon is in new moon phase, which is shown here, or full moon phase, which is shown here. So the high tide should be higher than the high tide here, and the low tide here should be lower than the low tide here. I think the picture, they didn't really show that good here. But if you look on pictures online, you'll see a little bit more spring tides. I'm trying to show you a little bit more exaggerated picture so you can see. I like this image. I really like this image. And it's also, can I stop it? No. So you can kind of see, I wish you could stop it. I want to find one where you can stop. Okay, so this is neap tide. See the first quarter? So the high tide is not too high. The low tide is not too low. You see? But then if you go to a spring tide, there you go. The high tide, you see, this is a little bit better picture. You can tell the high tide is higher than the high tide there. You see there? The high tide here is higher because the moon is pulling you in the same, stretching you in the same direction as the sun is. See, new moon, and then when it goes to the other side, it becomes full moon. So the full moon and new moon is the same. So you see the high tide here is higher than there, and the low tide here should be lower than there. Quite a bit lower, probably, you see. So you can kind of tell those are a little bit better pictures. Okay, so then comes the next exercise. Okay, so while walking to Boston, work in Boston, the Bay, what is the current phase of the moon? So this one again doesn't have too many questions. So just take a picture of the result for each one. When it's got like 8, 9, or 10 questions, then we just take the whole thing, and especially when it's something like the first lab where you're doing the same kind of questions like scientific notation over and over again. So we just take the picture of the final result. But these are like different kind of questions. So looking at a printed tidal chart, okay, so again, take a picture of your result for that. Okay, I think that's it for that. Cool. So this one doesn't look as long so far. Let's see here. The calculation at the beginning was difficult, though. More kind of harder calculation. Tidal forces, Roche limit. So the Roche limit is the limiting distance within which gravitational bound structures like planets and moons will be stretched to pieces and torn apart by tidal forces. Oh, like planets. So basically, if you go within the Roche limit of a planet, you might be stretched out. In other words, the tidal forces on you might be so strong that you will be stretched out and torn into pieces. So tidal forces not only determine the variation in ocean height on Earth, but they also have other important effects in many parts of astronomy. For example, tidal forces determine the minimum distance from a planet at which a moon can be located. In other words, if you were to take our moon and drag it closer to us by, let's say, 10 times, it might just break into pieces and turn into a ring. That'd be interesting, right? Having a ringed moon around us instead of a one single moon like Saturn's rings. So if you bring it close enough, it's shattered into pieces. It is possible for tidal forces to become so great that no large solid object held together solely by gravitational forces can exist. The distance from a planet or any other object at which this occurs is called the Roche limit. Solid objects that are not held together by some stronger non-gravitational force, such as chemical bonds, and that end up in an orbit inside of the Roche limit, will be torn apart by tidal forces. Conversely, solid objects cannot grow by gravitational accretion into larger objects if they orbit inside the Roche limit. In other words, if a moon started its life inside of the Roche limit, then it's never going to grow as into a moon. It's just always going to be a ring. You know, the gravity will not be able to coalesce that object, and it won't form into a moon. You see. So the animation is a visual explanation of the tidal disruption. Press the play. So let's see what happens. So here's a moon, and it's going to come within the Roche limit. Let's see what's going to happen. Notice that the way this tidal distortion, but no disruption. You see here, the way that they drew it, they kind of over exaggerated the drawing, but they're drawing it so you can see the tidal force on that moon. You see? And remember how I told you that the Earth will cause a tidal force on the moon? Well, this is, I think they're drawing Uranus or Neptune because it's bluish. So they're showing you the tidal force of Neptune or Uranus on one of its moons. That might have more tidal effect, especially if the moon is close and enough to where it might bulge it out more, you see. But the issue with this moon is that it's never going to fall into the Roche limit because it has a stable orbit. So it's never going to be completely torn apart, although it will be stretched out, you see. So then press play. Oh, I see. Then you see how the one broke into pieces? Let me go back. Focus on there. So it basically, hold on, let me minimize it. Yeah, I guess they didn't really show, but it might have even formed here and then gone inside of it. And then due to the tidal disruption, it just broke into pieces, you see. Watch that again. Boom, that's it. And then those guys are never going to coalesce into an actual moon one day. So the Roche limit can be calculated if one knows the density of each body and the size of the massive object. The general formula for the Roche limit radius is given as follows. Notice that if we can consider the densities of the two objects to be equivalent, the Roche limit takes a simple form. In that case, it is just 2.4 times the radius of the massive object. Oh, okay. So in other words, here's the Roche limit of this planet. You have to take 2.4 times the density of that planet divided by the density of that moon to the 1/3 power, cube root of that, times the radius of that planet. So notice that we don't need to know the radius of the moon. So if the two densities of the planet and the moon are the same, if this divided by this is 1, then 1 to the 1/3 power is still 1. Then that means the radius, the Roche limit is 2.4 times r. So that means I have to go 1, another 2, and 2.4. So basically here in the picture, they're showing you the Roche limit. What would the Roche limit be if that moon and the planet are the same density? If this guy comes within this, it'll be shattered into pieces. Okay. Now, what's going to happen if I make this density here smaller than the density of the planet? If that guy is smaller, then this ratio is going to become bigger than 1. You see, that's the kind of the idea. So try to see if the formula makes sense. If this guy is less dense than that, it's probably more likely to be broken into pieces because the material it's made of is not as dense. So if I take the ratio of this over this, and this is less dense than that, that number is bigger than 1. That means the Roche limit is going to be bigger than 2.4. That means it's going to be like that. You see? So if this guy was less dense than that and the Roche limit is here, it would already be broken into pieces right now. You see? So a less dense moon has to go further out in order to survive, in order to stay as a moon. It perfectly makes sense, right? So the less dense this is, the better, the worse it is for it to survive. The denser this guy is, you could get closer to it. You see? I mean, hold on. If you get, no, if this is dense, it's still dangerous. Yeah, if this is dense, it's dangerous. And if this is not dense, it's dangerous for the moon. But if the planet is not dense, oh, then the moon can come closer. You see? Okay, so Roche limit calculator. I think we're probably going to have to use this for this. Question 1. Given the Earth density as 5.5 and the moon's density as 3.3, determine the Roche limit for the moon orbiting the Earth in units of Earth radii. Okay, so Roche radius of planet, radius of planet. So can we use that that app to do our thing? Well, if given the Earth is 5.5, the planet density of planet 5.5, right? Density of moon 3.34. And the radius of the planet I'll just put as 1, because the answer that they want is in terms of the radius of the planet. Okay, calculate. 2.834. So notice in our case, the moon is actually less dense than the Earth. You see? So what was the answer? If they were the same density, the answer would have been 2.4 R. But because the moon is less dense than the Earth, someone has to go further away, 2.834, further away than the 2.4. They have to go that far away in order to be safe. So it's gonna go a little bit farther out. So an object would have to go 2.834 radius of Earth in order to be safe. So then question 2, what would the Roche limit be in units of Earth radii if the moon's density were 1, density of water 8, density of water, and 5.5, density of water 8 gram density of iron, and 5.5 the density of the Earth respectively. Oh, so what they're doing here is keeping the density of the moon, keeping the density of the Earth the same. So they're keeping this guy the same, 5.5, and they're changing the density of the moon only. They're making it as dense as water, 1. Well, that's going to make the Roche limit very high in terms of the Roche limit is going to go. So this is going to go basically change to 1. Oh, I see you have to go farther out. So imagine if the moon was literally made of frozen ice, kind of like Pluto, but like completely frozen ice. Then it would have to go 4 times further away than the radius of the Earth in order to be safe. And then if it was iron, it could come in closer, right? If it was denser. And then what if it was the same density as the Earth? And then question 3, what is the Roche limit for the real moon if the Earth were made entirely of iron? In terms of, so now what they're doing is they're going back and saying, well, let's keep the density of the moon the same, but now let's make the density of the Earth like iron, you see? So they're changing it up each time. What would the Roche limit be if the Earth had the same mass, but its radius was increased to 1.5? First calculate the density of this new larger Earth. Density of new Earth. Oh, okay. So then they're saying, keep the mass of the Earth the same, but change its radius. So planet, radius of planet, in terms of so basically this is going to be 1.5. Density of the planet. So then you're going to have to calculate the new density of the Earth if it was 1.5 times greater. Now use this new density and the new radius in the calculator above to determine Roche limit for this new larger Earth. Okay, so for this one, you could pretty much use most of these. You could use the app. The fourth one, you're going to have to show your work on how you're calculating the density of the. So here's what I want you to do. From questions 1, 2, 3, choose one of them to show your work for. Except this last, don't do this one because that'll be too easy. So show your work for either this one, or this one, but not that one. That's if the density of the Earth, that's that basically if the density of the moon were the same as the Earth, so it's too simple. So one of those three, right? The rest, use this to calculate it. So each time take a picture of this. So here it is. So this one, put in the values here, take a picture of that. So that's one snapshot. Then put in your answer, submit. That's your second snapshot. Then you go to here. You go to the top, you put in your numbers, you get a snapshot. Then you put that answer here. You go to the top, you put a numbers, put your answer here, put your answer here. So that's 3 more snapshots. Then one more snapshot for the whole thing, what you got, right? Then show the work for either this one or the one from the first one. Then you go to question 3. This one, you don't have to show the work for because it's similar to the questions 1 and 2. So then you just go back up and put in that, put a snapshot, and then another snapshot for the result. Then you go to the question 4. Now show your work for how you're getting this. That app is not going to give you that. You're going to have to calculate the new density of the Earth, given that its mass is not changing, okay, in grams per cubic centimeter. Its radius is changing to 1.5 Earth radii. So then calculate its new radius. So show work for that. Then go to that app, put in the values, and then get an answer here. And then take a snapshot of the app. So take a snapshot of the app for that, and then put in the value here, then submit, and then get a snapshot of your results. Okay, so basically one more snapshot for this, and then one more snapshot for the whole result. And I think that's it. Yeah, I think that's it. Let me show you how you would get something like that, but not necessarily that. So let's say I were to keep the Earth the same mass, but change its radius to 2.5 times what it is now, or 2.25 times, anything. How would you approach a problem like this? So if you keep a planet, let's say this is the Earth. Now imagine I keep the Earth the same, but now I make it 2.5 times bigger. So that literally means you can take this here and put two of this. By saying 2.5 times, this is what I mean. Does it make copies? So imagine get another. Yeah, so something like that. You see, if I were to make the Earth 2.5 times bigger, that means you could fit one Earth, another Earth, and then half of another Earth. That's what it means to make the Earth, the radius of the Earth, 2.5 times bigger. You can fit 1, 2, and then a half. So then what would it happen to its Roche limit? But we're not changing its mass. So then what's happening to the density? So the density is equal to mass over volume. Over volume. And the volume of a sphere is 4/3 pi r cubed. So if I make the planet Earth 2.5 times bigger, I'm just changing the radius to 2.5 times r. Right? So then the density, since the density is inversely proportional to the cube of the radius, if you make the cube 2.5 times, you have to cube this 2.5 to the 3rd power. I don't care the 4/3 pi. I just care what happens when you cube 2.5. So I'm going to go to the calculator and cube 2.5. 2.5 to the power 3. It's 15.625. So then what's going to happen? The distance. So then m over 4/3 pi, and then r cubed. And then 2.5 cubed came out to be what? 15 point, what was it? 15.625, okay. $15.625. So how is that going to change its density? Well, the ratio of mass over volume is its original density. You see, that's the original density. So what is that? Well, the density of the Earth is 5.5. That number is already given. We already know the regular density of the Earth. Then you divide that by 15, by a factor of 15. In other words, if I make the Earth 2.5 times bigger, I'm decreasing its density by 15-fold. So it's not going to be a very dense planet anymore. It's actually going to be less dense than water at that point. 5.5 divided by 15.625. Man, that's crazy. Its density is going to be 0.352 gram per cubic centimeter. The density of water is 1 gram per cubic centimeter. So if you could do something like that, you would have made a planet that will float in water. So now this is the new density. So what should be the Roche limit to that planet? Well, since it's not very dense, a moon should be able to come very, very close to that planet. You know, it'll be still safe because its density is so little. So then you go to the Roche limit equation, and then you could put in the numbers into that app there. For that one, you don't have to show the work because it's the same kind of calculation for the Roche limit. So then just put it into the app and have it calculate for you how many Earth radii you have to be safe. So there you have it. I think that's the last thing. A lot of math there, but a lot of good stuff. You can kind of see all of this where it comes from is Newton's law of gravity and the analysis of tidal forces. And I think tides are very important. It's possible that without tides, maybe life would not even exist. I could venture to say that. Let's see, was that the last thing? Yeah, I think that's the last thing. Yeah, the tide without tidal forces, life would not possibly exist. Um, so that you could see tidal affects other aspects of oceanic life, including reproductive activities of fish and ocean plants, floating plants, and animals ride the tidal currents between the breeding areas and deeper waters. But of course, you can say something like, well, if there were no tides, maybe life would have developed that can live without tides. That could be. But at least to our life form here, tides are so important. And I don't think without that, life would keep sustaining itself. So now you know all the mathematics and the physics and all the aspects of tides, backwards and forwards, hopefully. Okay, guys, thank you.